Okay, photovoltaics 2.1. In this chapter, we're going to talk about electricity, what electricity is, Ohm's law and Watt's law. I wasn't going to put this video in there because there's so many good videos on what these particular things are and how to use them, and that aren't mine, but just for the sake of rounding the whole thing out, we're going to go ahead and put this video in there. What is electricity? Electricity is the flow of electrons through a conductor that does or does not do useful work. Many people like to use the analogy that it's like water flowing through a pipe and current is like the pressure of that pipe. I think that's a crazy analogy. I never understood it. It falls apart. So I got my own little analogy. It's worked for me. It, maybe whatever. Okay. All right. This is potentially a waterfall. There's water up here, there's water down here. This distance in my mind is like the voltage. It's the potential difference between particles with one amount of energy and particles with a different amount of energy. Current would be like if water actually flowed over this waterfall. See, if there's just water at the top, if you raise water a long way, you have a potential difference. It has the potential to do work. It might not do anything. But, and the further you raise it, the higher you get that, the more potential it has to do work. The potential difference between the two is higher. You'll hear a lot about potential difference. If you actually let a little bit of water flow, maybe over a wheel, there's a little wheel there, you can actually get some work done. Now that part that's actually doing a little bit of work, that's current. The amount of water, the amount of intensity water going over those falls is the amount of work you could get done. If you have water that's very, very high up with a very, very high potential difference, but only a little bit of it comes out, you'll get, some amount of work. If you get water that's not very, very, has a low potential difference, not very high up, but there's a lot of it, you can get, some amount of work done. It's the ratio of the two that really matters. How much potential difference can you get and how much can you push through? That's always been the difference. So in my analogy, voltage is like the height of a waterfall, where current is the amount of water actually flowing over the waterfall. Voltage is the potential difference between the top and the bottom. Intensity, the current is actually the amount going over. That's the analogy I worked out. I used it. It worked for me. Okay, so now that we're kind of clear on what electricity is, some definitions that you might need, some definitions that are going to help, move this forward. E is electromotive force. It is a measure of the potential difference. It is measured in volts. It is the voltage. Electromotive force measured in volts. I is intensity. It's measured in amps. Symbol is A. Resistance is R. Symbol is ohm. Symbol is omega. It's measured in ohms. Power. The definition of power is the electromotive force times the intensity. It is the voltage times the amperage, is measured in watts. Power, although it's not it's not an entity of its own. It's made up of volts times amps. It's an extremely useful term to use because it you'll see why actually when we get into circuits. All right, so that's for you. I'm gonna go ahead and move this. All right. we're going to talk about Ohm's law. Now, Ohm's law simply states that voltage is equal times the amperage times resistance. Okay? Or all right. And why do you write it VIR? Well, to me, this actually spells the word man in Latin. I was a Latin nerd when I was a kid, so this is how I remember it. The triangle. This particular triangle is it's a tool. You can use it because if you want to find out any one of them, you just cover the one that's missing. Okay, like this. You want to find voltage, you cover voltage. It says, current times resistance. You want to find out current, you cover that one up. Voltage over resistance. In the same way, you want to find out resistance, cover it up. Voltage over amperage. It's just a neat tool. All right. So Ohm's law says that voltage is equal to amps, so multiplied by ohms. You can, of course, flip this around, using a little bit of math in the way I said. E equals I times R is the same as, dividing both sides by R. And, voltage over resistance equals amperage. All right. How do you prove Ohm's law? I don't know. But it's worked out every single time I've ever used it, so it works. How's that? That's good. Because this is my video and it's opinion-based, I just want to say a word about Mike Holt. Mike Holt's a very famous electrical instructor. He has a bunch of videos and a bunch of instructional information, and Mike Holt is a fucking tool. He needs to never teach anyone anything. He's a homophobe. He hates people with tattoos. He hates women. I went to his seminar 2 weeks ago. That guy is the most hateful Christian I've ever met. I'm not a Christian. He's not allowed to judge because he is. I'm allowed to judge because I'm not. I hope that dude burns in hell. Worst 2 hours I've ever spent in my life. I hope that someday he goes out of business and that no one ever has to suffer through him speak again. Okay, sweet. Watt's law. Watt's law basically defines a watt. What is a watt? Watt. Okay. Watts equals voltage times amperage. It just defines what a watt is. Now, the reason a watt is useful is because that ratio, the waterfall, the height times the volume, well, if you have a much higher height and a much lower volume, you can actually get the same wattage, the same amount of power as you could with a much, lower potential difference and a much higher current, or a much higher potential difference and a lower current. And this is useful when we're going to wire things into series and parallel connections right now, so you can see the way things work. It means that you can wire things in different ways, get different voltages and different amperages, still come up with the same wattages, which is great. Which means things you can measure in watts don't necessarily have to be producing, the same voltage and amperage for them to match up or be useful. Okay, so the other effect of having this Watt's law. if you combine Ohm's law, V equals, amps times ohms, and you kind of stack it into this Watt's law, right? So
what is a volt?
What is a watt equal? An amps times an ohm.
A volt times an amp.
A watt can equal, a volt equals amp times an ohm. 1 amp times an ohm times another amp. And you have a watt equals, the amperage squared times the resistance. And in the same way, you can use, algebra to change the watts and Ohm's law equations into all of the equations in this little circle right here. You can actually just derive them. You only ever need to know, wattage is equal to voltage times amperage, and voltage is equal to amperage times resistance. And you can derive all of these different ones. This little circle is useful. You'll see it a bunch of times. Just, as a little guide. They're set up into corners. So like this corner right here is, R for resistance, and it'll show you, voltage squared divided by power equals resistance, voltage divided by amperage, resistance. Power divided by amperage squared equals resistance. And, the same goes with all of them. If you memorize the whole thing, good on you. If you don't memorize the whole thing, you can just derive the formulas pretty quick. Okay, so current. We learned about Watt's law. We learned about Ohm's law. Let's learn a little bit about current. Current, as you recall, is the intensity of electrons flowing through a given conductor. There's two ways they can really flow through that conductor. One is DC current. DC stands for direct current. Plotted along a graph of voltage, the current will be usually greater than 0 and will flow continuously into a straight line. It will be a certain distance above 0, maybe 120, and will go continue over time, if this is time. On the same graph, you have AC, which stands for alternating current. 0, you'll have like 120 up here, you'll have negative 120 down there, and the current will fluctuate. Now, most of the time you'll see current fluctuate in a sine wave when it's drawn. It's a little example down here. Other AC waveforms, you can have square waves, you can have sawtooth waves, you can have like a noise wave, which is pretty random. You can have a modified square wave, which looks like little stairs. And we'll cover those when we go cover inverters. And just so you know, this isn't the only wave it can have. The differences, the benefits of each. DC is easy to work with. Edison considered it to be safer. It's easy to measure, and it measures out in all the math that we just covered and the future math. If you measure the current, everything is going to work out okay. All the calculations are going to work out. The power calculations are going to work out. The inductance, they'll all work out. Everything will be okay. AC current is, the way they receive an AC current is mostly through spinning a turbine. And what happens is, as it breaks the magnetic fields, it breaks them, as it breaks forward through the magnetic fields, you'll get this big positive voltage. As it passes through the 0 point and start passing through the field in a negative direction, you're going to get this big, you're going to get all the way down to the negative. And as it cycles through, it'll go back positive, negative. And since it's a turbines are basically circles. What we have is basically a sine wave. You turn a sine wave, in half, you fold it in on itself, it makes a big circle. It looks like a turbine. That's a little bit simple, but awesome. The way we get DC electricity is we get it from photovoltaic cells. A DC current is the way is photovoltaic cells generally, or batteries. It's important to keep these two separate. If you were ever to go between the two, and you can, a lot of what we do in photovoltaics is travel between DC current to AC current, because houses are generally wired with AC current. Photovoltaic cells produce DC current, and so we need a way to go back and forth between the two in a productive and useful way. The way we do it is from DC to AC, we use an inverter, and from AC to DC, we'll use a rectifier. Okay. One more thing about AC and DC current. AC current is not the easiest thing to measure, because instantaneously, as these values change, you will have different voltages, right? Okay. Okay. So if you measure right here, you're going to get a measurement of 170 volts. An instant later, 120, an instant later, 40, an instant later, 10. And then if you were to measure it instantaneously, there's a potential, even though there was a good deal of current going through it, you would read 0, because at that particular instant, there was 0 current. Okay. 0 voltage. And as it goes below that, as it passes through the midpoint of the electric field, it starts producing negative voltage. Negative voltage has the same potential to do work as a positive voltage, and so there you go. All right, so it'll measure negative 10, negative 40, negative 120, negative 70. And so the way we need to understand the calculations of this is that the AC current is measured in an RMS value. That means root mean square. That means you take the square root of the mean and you square it. When you square what it does is it turns everything into a positive number, averages it out, and gets the root of that. So the magic number for a sine wave, and the one you'll use most often, is 0.707. 120 volts is, you take the peak value, you multiply by 0.707 in a regular sine wave, you'll get the RMS value. And there you go. All right, so you may never ever use this during photovoltaics. It's just important you know that the actual instantaneous value of your AC in an AC current is not the thing you're measuring. What you're actually getting is an RMS value. That's the thing that's going to show up on your meter when you test, and there you go. Okay. So series and parallel circuits. I'll bring this all together and show you a little bit about series and parallel circuits, how we're going to wire PV panels and batteries together to get different voltages and amperages, and then you'll see why all this math is important. Again, I'm not an authority on any of these things. I'm going to screw something up, probably have already. There's a lot of really good videos. I want to big ups to khanacademy.com, CHAN academy.com. If you have problems with any math, any algebra, trigonometry, calculus, anything, just go to his site. His videos will explain everything to you, and they're wonderful. So, okay, cool. Okay, series and parallel circuits. A series circuit. A series circuit means that the power going, little couple definitions. Okay, so that's going to be a battery. Usually they, the short line, the long line, short line, long line, that represents two cells in a battery. Generally they're labeled, so many volts. Okay. When there's a line drawn in a diagram, that's usually a wire or, a line on a printed, okay. This is not really a schematic symbol. The light bulb. Show you some more schematic symbols as we go along, I'm sure, but a little battery right here. Okay. A series circuit. A series circuit means from, the positive connecting through the negative, it goes through from one to the other. All the different things in this part of the circuit go into one, out of that one, into this one, out of this one, into that one, and then this is the thing. What's a circuit? I think you guys probably already know. A circuit means it completes a full circle. Electricity doesn't flow unless it completes a full circle. So you always have to start with the power source and end back at that same power source. Start at the power source, end with ground. So, series circuits. If they're all in series, that means that any break in this circuit, say there's a break right there, will shut everything down. What it also means. It also means that the voltage throughout this circuit will be different. You will read a number, let's say through here, you put a little meter on it, you read 12 volts. Okay? And that's right there. You put a little meter right here, it's going to read 4 volts. A little meter here, it's going to read 4 volts. A little meter here, it's going to read 4 volts. Okay? The law is this voltage drop, the total voltage drop that you have in the battery is going to be represented in the total set of voltage drops you have. Okay, sorry about that. My microphone went out. Let's do it again. Okay, so series. We just finished going over basically series loads. Let's put some PV panels together. PV panels are sometimes drawn like this, just, because they're square and they get connected at one end. Just as connecting, those light bulbs in series, all you have to do is connect the negative to the positive in all of these, and they'll be connected in series. Just like that. From here, positive, negative, positive, negative, positive, negative, positive, negative, positive. These are all 12 volt, 5 amp panels. Okay. Because they're connected in series, still going to have 5 amps. And you're going to have 48 volts. You connect things in series just like with the loads. Volts changes, amperage doesn't. All right? Okay. Parallel. All right. Parallel circuits. Start with battery. Put a couple of those in there. Now, these are in parallel because if you were to break several parts of this, say you were to put a break in this wire here, or a break in this wire here, the other section of that would still continue to be a circuit. It would still function. Also, these lines tend to look parallel when you draw them. Also, there's some other things. Let's just pretend. So 12 volts, 5 amps. 12 volts, 5 amps is going to be this power source. Now, if you were to measure right here, you get 12 volts. Because basically you're just measuring here. It's just a wire that connects these two. Same over here. You know? So the voltage drop across this light and this light, all the same. It's 12 volts anywhere you measure it. However, 5 amps? No, I don't think so. This one's 2.5 amps. This one's also 2.5 amps. The sum total, I mean, the rule is the amperages going into any given section have to equal the amperages going out of that section. All of these amperages have to equal up to this amperage. It's just, you know, the way things roll. So, all right. PV panels are exactly opposite. I mean, well, or exactly the same, but with gaining power. Now, you know, the way you put these together in parallel is you take all the negative ones out. Take all the positive ones out. These are all 12 volts, 5 amps too. Okay. Because these are put together in parallel, it's going to come out at 12 volts. But these amperages are going to stack on top of each other, just like these two amperages stacked on top of each other. 5, 10, 15, 20. It's going to be 20 amps. This cell is the same as this cell. This cell came out at 48 volts, 5 amps. This cell came out at 12 volts, 20 amps because of the way it's wired together. Show you one more example. The same 4 cells. Put these two together in series. Put these two together in series. That means this 12 volt, 5 amp. These two sections, the way they're put together right there, that's going to make it 24 volts, 5 amps. This is going to be 24 volt, 5 amp section 2. You connect those two together in series. Bring the positive ones out right there. The negative ones out right here. What you have? 24 volts, 10 amps. These are the same 4, components. There are 4 cells that are 12 volts, 5 amps. You can get a 24 volt 10 amp system. You can get a 12 volt 20 amp system. You can get a 48 volt 5 amp system. And, the important thing about this is all of these systems, as you recall, power is simply voltage times amperage. Take 48, multiply by 5 amps, you get 240 watts. You take 24 volts times 10 amps, you get 240 watts. 12 volts, 20 amps, 240 watts. It's useful to use wattage to measure panels and to measure systems, how big systems are going to be, because no matter how you wire them together, you can get different voltage, different amperages, but these 4 12 volt 5 amp panels are always going to give you 240 watts, no matter how you put them together. So, all right, so that was pretty much the end of this video. I hope you learned something about electricity, Ohm's law, Watt's law, a little bit of math, AC and DC, current, and a little bit about series and parallel circuits. Next one we're going to do is about the sun. Photovoltaics is half about the sun, so we're gonna deal with like Earth's rotation and azimuth, zenith angles, irradiance, irradiation. We're gonna do that stuff. All right. Thank you very much.